we assume that this P is divided into two halves, left half and right half. Okay, and we assume that uh, we can somehow compute the closest pair in each half recursively. And then if we can find out the overall closest pair in order n time, that means if we can merge, okay, the two subproblems or solutions to subproblems in order n time, then we are done. Okay, so that is roughly the idea. Now, what we assume for processing of this entire thing, we need some assumptions or data structures. So what are the assumptions? Let us assume that the function, okay, so we have the P. P is the given set of n points. Now, if you look at P, just by P, you cannot conclude anything about the points. I mean, these points are random. Okay, so for that, let us take, let us assume that from P, we can derive two things. One is Px. What is Px? Px is the same P, but sorted according to x coordinate. Okay, and from P, we can again derive Py, which is the same set P, but now they are sorted according to y coordinate. Okay, so that means they're sorted along this line, and this is the Px, and sorted along this line, that is the Py. Okay, so these two sets we can form. Okay, these two sets we can form. So, how much time it takes to do that? Probably we can do this sorting in order n log n time. Okay, both these things we can do in n log n time, because if we just execute one n log n sorting algorithm on this P, then we get Px and Py. Okay. Now after these two things, uh, we actually have to have some mechanism. What is the mechanism? Mechanism is, let us say this is Px and this is Py. Let's assume. So what is this Px? Px is actually all these elements in sorted X order, and Py is all the same elements but in sorted order. Remember, the ordering in Px and the ordering in Py, they may be totally different. I mean, only the content-wise, the total number of elements and set of elements, both the arrays, they are same, but their positions may differ actually, because they are sorted based on different things. Now, what we assume is that each element here. So suppose this is an element, okay. Now this element occurs fourth position from the left in the Px, but it may not occur fourth position from the left in Py. It may occur at any random position based on, because this is y sorted. Let's say this position. This is the position. So what we do, we make an arrangement. Okay. So this you can think of this is a record or array of records. So this has a pointer pointing to this. Okay. Similarly, this will have a pointer uh, indicating this is present here. So that means what? That means from this element for every element in Px. I know what is its position in the array Py and vice versa. I know that. Okay. So that thing is there. So how to do that? Probably we can do that in linear. Okay? We can do that in linear time, not more than that. So once I have this thing, then so this is something prerequisite to do the problem. Okay, in a divide and conquer way. So after that, what we do, we we uh, we assume that let Q be another set, Q be another set of points, which is first n by 2 So uh, what is this? See, the set wise, if you look at set wise, then this P, Px, Py all are same. But ordering wise, P, Px, and Py all different. But since set wise all are same, I just start with this Px. I feel that okay, if I feel comfortable with Px, you can start with Py also, it will be similar. So let us start with Px, the same set of points I start with. And I assign Q be the first n by 2 points in Px. So Px is sorted and I just divide it like this. I just make a division. So first n by 2 points in Px. So this essentially what it means to this picture. I make a imaginary partitioning like this. And I make two partitions basically. Okay. So now what I have R remaining half of Px. So that essentially means this part is roughly my Q, this part is roughly my R. Okay. So once I have this thing, okay, once I have this thing, so now look at the Q and R. See, Q and R, Q is first half of Px, R is second half of Px. So that means Q and R are smaller parts, but I can see that Q union R is essentially equal to P. I can say that. Okay. So that is very easy to see. Now, what I want from this Q and R is I form a couple of sets. What is that? One is QX, QY, RX, RY. I form this set. What is QX, QY? QX is actually the Q, the same set Q, but sorted according to X coordinate. QY is the same set Q sorted according to Y coordinate. Similarly, Rx and Ry. Remember here, what is my Q? Q is the first n by 2 points in Px. And Px is already sorted in X. order. So essentially this I can say this is equal to Q, because Q is this and Qx is same as Q. But see Qy, what is that? I do not know. That essentially I have to sort this part, because it is the same set Q, but now it has to be sorted according to Y coordinate. Okay. Rx similarly, Rx is essentially equal to R, but what is Ry, that I am not very sure. I have to calculate Ry. So question is how quickly I since I have Px and Py already I claim that by a single pass, by a single pass over Px and Py, we can calculate Qy and Ry. Okay, why so? Remember what is Qy? Qy is essentially the sorted version of Qx according to Y coordinate. Now this is the sorted version of Y, Py. So what I do, I just go through this Py left and right. And you remember every point in Py has a pointer here, right? So now I will see those elements in this Py which has pointers up to this first half. Okay, this may have pointer here, this may have pointer here, etc. It may have many things. Okay, those who have pointers up to this first half, they are considered. So what I will do, I will just scan left to right from Py, and if it points to any element up to the first half of Px, okay, then that element I will pick and I will just put them in Qy. Okay, because that must be this set of elements only, but now they are segregated in the Py. So once I make a left to right scan in Py, and I just pick up those elements from Py whose pointers are pointing to the first half elements of Q, I mean first half elements of Px, or they are pointing to Q, then I am done. So that's why it is said by a single pass over Px and Py, we can calculate Qy and Q and Ry. What does this mean? That means, see, I sort these. Okay, I I sort this Px Py. That time it took order of n log n. But after that, okay, after that, to calculate this Qy and Ry, I do not need to sort them again. I just scan left and right in this Px Py, and I can do that in order n time. Okay, okay, fine. So this is clear, right? So once I have this couple of things, then what is my point? My point is I now have two parts. If you think of, I now have two parts. One is this Q part, one is this Q part, another is R part. And Q, I have two things. I have QX, I have QY. R, I have RX, I have RY. Okay. So I have all the data. So what I do is I find out the closest pair in this Q region, and recursively I find out the closest pair in this R region. And let's say the closest pair in this region is Q0, So this is, let's say we designate two special points, Q0 star, Q1 star. Okay, like this pair. So such that Q0 star is actually an element of Q, Q1 star is an element such that they are the closest. Similarly, I can say R0 star, R1 star, okay, is the closest pair in this site. Remember, how do I get this? I actually call the function recursively, okay? And there is some base condition. What is the base condition? We'll tell later. So recursively, we find out this closest pair in the subregions, okay? Now, once I have this thing, okay, then I have a critical question. The critical question is, with these things, okay, with these things in hand, I have to combine and I have to find out the combined closest pair. Okay. So for that, we say let delta be the mean of d q0 star q1 star and d r0 star r1 star. What does it mean? Let this small delta be the minimum of these values. So out of these two closest pair, which one is delta? Delta is the smaller of these. Okay, delta is the mean of these. Okay. Now, if I have a q, if I have a q in a, which is in q, capital Q, and in R, which is in capital R, if I happen to find such a q and R such that distance of q comma R is actually smaller than delta, okay, then we know that this QR is the final closest pair. Otherwise, delta represents the distance of the smallest closest pair, and this corresponding item is the closest pair. That means if delta is this, then Q0, Q1 is the closest pair. Otherwise, this R0, R0 star, R1 star is the closest pair. So if we find that such Q and R exist, that is such that they are smaller than the minimum of these two, then that is my new closest pair, final closest pair. Otherwise, anyone with delta is the mean, which one represents delta, that is the closest. Okay. Now, what I have to do, I really need to check whether I can find such a Q comma, okay. Can I find such a Q comma R at this point? That means after dividing it in this way, what is the way? What is the way? What is the way of division? You remember? I divided in such Q and R, where Q is the first half of P and R is the second half of P. So there's nothing wrong in my division. Okay? So how I divided, like, so now what I do is you think about this division. This is an interesting thing to understand. So this is my division, roughly the division, where this is my Q, this is my R. And this whole division is based on something known as PX, which is again is equal to, so this is entire P, and this side is Q, and this side is R. Okay, and these points are separated. Now, see, this line is said that the first half ny2 ceiling. Right? Okay. So whatever it is, I consider this. What is my Q? Q is the sorted points. Q is essentially equal to Qx. Okay. Then I can say let x star be the x coordinate of the rightmost point in Q, which is equal to Qx. Let x star be the x coordinate of the rightmost point in Q equal to Qs. Rightmost point means, see, it is not the vertically thing. Any point has two coordinates, x and y. So rightmost means the closest, actually, close to this line. So that means which have the largest x coordinate value. That means that it is the last point in the x sorted list. Okay, x star, that let that be x equal to x star. Okay, so if that is the thing, then let us assume that there is a line L that is denoted by this equation x equal to x star. So x equal to x star is the line like this. So I draw this vertical line, x equal to x star. That means what? That means this is the rightmost point, and its y coordinate may be anywhere, but x coordinate, actually this point may be here, x coordinate and y coordinate, because if x coordinate is this, y coordinate is, that's why the point is here. The point is on this line. So what I do, I just find out the rightmost x coordinate and draw a vertical line, and this line I designate as L. Okay. So I can now say that this line separates Q and R clearly, because all the points that are in Q, they are either on the line or on the left of the line. Okay. On this left side, and all the points in R are strictly on the right side. Why so? Because the designation is x equal to x star, that is the highest x coordinate. So that means only one point will be on this line, and rest other all points will be in this side. For the time being, we assume, let's say that, okay, I mean, all the x values are distinct. I mean, they do not match. I mean, they're unique elements. Let's, for the time being, assume. So all the elements in R actually to the right side, because if some of them are on this line, their x coordinate will be here, so they will not fall here. Because how we define partition Q and R? Like the first n by 2 and the second n by 2. Okay, in the Px. So I hope this is clear. Only one point in Qx is on this line, and rest other are all here, all in the left. All points are in actually right side of this line. Okay. Now we claim a lemma with this construction. We have a lemma that what is the main thing? We said that if we find such a small q and small r, such that their distance is strictly less than the delta. Delta is the smallest of these two recursive distances. These distances found in a recursive way. Then that is the final closest pair. So the lemma says, if such a thing exists, I mean, if there is a q which is in Q, and there is a small r which is in capital R, okay, such that distance of these q and r is strictly less than delta. If this happens, then q and r lies within a distance of delta of this line L. So what this means? This means make a, what is delta? Delta is the closest pair in this region and the closest pair in this region. Delta is the closest distance. I should not say closest pair. Delta is the minimum of these two distances. So that means, let's say I draw another vertical line which is at a distance delta from this line, and let us say another vertical line which is at a distance of delta from this line L. So the idea of the lemma is this: if such a Q and R, okay, has to exist, then where their distance will be smaller than delta, then they must lie within a distance of delta from this L. Okay, why so? Because suppose it actually Q lies here, okay, and this is my Q, and R lies here, suppose, okay, so R. So actually, what is their distance? Their their Euclidean distance is this, and their x distance is y distance is this. Okay. So x distance, they are separated by at least 2 delta. Okay. So x distance, they are separated by at least 2 delta, and y distance, they are separated. How much I do not know actually. Okay. So if x separation is more than 2 delta, then I can say their Euclidean separation is 2 delta square plus something. This y distance is suppose some z y. Let's say y. So y square. So since y is at least, let's say y is some non-trivial, so I can claim this is actually greater than 2 delta, basically. So if their x separation is more than 2 delta, then their actually physical separation or the Euclidean separation will be more than 2 delta. That means they cannot beat the distance delta in that case. Okay. So only if their, I mean, it may so happen that that means what? Their x separation and y separation should be such that their Euclidean distance separation actually is smaller than delta. Then only we will consider them as a potential point. So the main thing is that we need not search this entire space for such a small q smaller pair. We can search in this region, this shaded region. We can search in this vertical shaded this region. Okay, we can search this region only, all the points in this region, in this vertical strip. Okay, and check whether there, take all pair of points. Let's say this vertical region I designate as this vertical strip be, let's say, strip be S star. I designate. So I actually need to check all pairs of points, let's say x and y, such that x is an element of xy, both are element of S star, and distance of x comma y is actually less than delta. I should just check this. Okay, this lemma you can prove easily. This lemma is not difficult to prove. So I need to find out all such x and y. Now the interesting thing is that we should search x and y in this narrow band S star, which is actually delta separated from the line L. Okay. Now, how many points are potentially there in S? Okay. Definitely, I can clearly claim that this S star, which is a subset of these P set of points, which is essentially Px, you can say, but it's the subset of points. Okay. Now, what is let Sy be all this set of points in this stripe region. So when I have S star, this S star is again, is a set of points. So I can actually find Sy. Okay. Okay. First of all, how do I get S star? Okay. So basically, all the points whose x coordinate value lies between x star minus del less or equal to x star plus del. Okay. All the points. Okay. So you can actually go to the point, go to this px, go to this px. Okay. You have this. We have this px. Okay. And if I just scan through this px once, left and right, left to right, and I collect all the points that follow this condition, these conditions, whose x coordinate value falls between this x star minus delta and x star plus delta. Then those points actually I put in this star. Okay, that is my stripe region. Okay, now how many such points are possible? Of course, linear number of points are possible. O(n) number of points are possible. Because this is a subset of this, so potentially there may be many points which are actually in this stripe region. Now, of course, I mean, I can have their sorted version, I can have their sorted versions like this. This is my S star, okay? Then from it, I can have two things. One is Sx star, another is Sy. What is this Sx star? Sx star is actually the sorted of x S star in the x coordinate, and that is essentially the S, because I have picked up them from Px, but Px is already sorted according to x coordinate. Only thing I worry is I do not have this thing. I do not have Sy. Okay. So what I can do is, of course, I can achieve this Sy star by looking into Py, and I can pick up those points, okay, in O(n) time. Okay, so I do not need to sort S star. I can just go through Py and I can pick one by one, and I can sort them. I can get the Sy star in O(n) time. Okay. So once I have that, okay, this is now obvious. I mean, this lemma is now obvious that I actually need to find 2 points. I need to find 2 points, Q and R, okay, Q and R belonging to this S star, which is essentially equal to, you can say, Sx star, which is Sy star. Because the set wise all are same, but coordinate wise, I mean, order wise, they are different. I just need to find out these 2 points in this, such that if distance of QR is less than delta, I just need to check that, because if I find them, that means I know I have a new closest pair. Okay. If I don't find, I just declare the points that resolves this delta. That is the closest pair of the overall. Okay. Now, how do I find this DQR? I mean, I want to find out the existence of this small q smaller in this. Okay. Now, if you just look here, what are the points in S star? I said this set. All the points in Px that have x coordinate between x star minus delta and x star, and this potentially may have actually order n points. Okay, order n points. It may be half points, n by 2 number of points, n by 3 number of points, or n by constant, but that is still order of n for a large n. So this set Sx may have actually order n points, and to find such a closest pair Q and R, one may naively think that since there are order n points, I actually need to look all possible pairs of points in S. So one naive approach, maybe look for all possible pairs of the form, say, S in capital S star. Look for all possible pairs and then check if their distance is smaller than delta. Okay, but see, since this has on number of points, so all possible pairs will have actually on square possible pairs because n choose 2. So therefore, this calculation will be a bottleneck. Okay. That means what? My Fn, which we talked about in the last class, will be a problem. Okay. So this naive approach will not work. Okay. This naive approach will not work. So what's surprising, one interesting lemma that helps us here is very important, and we need to prove that. So why it becomes n square? Because for every point here in A star, okay, I'm actually comparing it with all the other n minus 1 points, all the other order n points for the search of this potential Q and R. But this lemma says that just like here, this lemma, this lemma says that if such a Q and R should exist, they will lie within a distance of delta from this line L. Okay. Similarly, this lemma is another powerful lemma which says that if such a Q, if such a pair of points S and S star should exist in S, such that their distance see, here I'm using S and S star because I'm now in this S. You can use P, Q, and R also, but this is something just change of symbols. If S and S star belongs to S such that their distance has to be smaller than delta, okay, then S and S star are within a constant positions. Constant, this constant can be something between 8 to 15. constant of each other in the sorted SY star. So this is very important. This is very important lemma, which essentially says it's like this. Let's say this is SY star, that is the sorted version of the SY, sorted version of the S star in the Y order. So what I will look is for the every point in this, okay? If such a Q and R or such an S and S star, S prime are to be there, then if I am interested this is, I assign this as my S, then what I do, I check the next, say 8 to 15 positions. Let's say 15. Let's say 15 position. I do not need to check the entire array. I check a constant number of next 15 positions. Okay. And I compare their distance. I calculate their distance and I check whether this is smaller than delta. So basically for every S I compare, I need to check another 15 points in this sorted one. Okay. So how many points are there in this list? There are order of n points. And for each of them, I need to actually consider next 15 points or previous 15 points. So overall time requirement will be order of 15 times n, which is essentially some order of n. So that essentially is the beauty of this lemma. It claims that if such a pair of points has to be close enough that their separation is smaller than delta, which is the smallest found so far, then they must be within this constant points, constant positions of each other in the sorted SY star. Okay, this is an important lemma. We need to actually understand this, or we need to. This requires some inner understanding. Okay, so let me try to give an outline of the lemma. You can find this in the book. Okay, uh, so but let us I mean let us just so you will see in the divide and conquer chapter. Okay, in the Kleinberg Tardus book. Okay, there's a divide and conquer chapter which is starting in the 5th chapter, and there is this closest pair of points problem. It is in page, starts in page 225. Okay, page 225 in Weinberg Tardus book. Okay, so you can check the lemma. Okay, so I give you a small hint actually about the proof of the lemma. So what is the idea is that this is the line L, x equal to x star. This is the line L. And only remember, only one point is on this line. This is my Q region. This is my R region. And this is my delta region. Both sides, this delta. Okay. Okay. This is delta and this is delta. So what I do is I just partition them equally. Okay, maybe this drawing is not proper. You should understand. I just partition it such a way that this is actually my partitioning scheme. This is my partitioning scheme, such that this small square. So it is partitioned into small squares like this. This is delta by 2, and this is again delta by 2. That means this is delta by 2, and this is also delta by 2. So that means so this is my partition. Remember, let's say this is my left line, this is my right line. Okay. So every point must be within this line, but I again further partition these points. Like I draw further imaginary lines like this line and these two lines I draw, and I make boxes of square boxes of a side delta by 2. Okay, so everything is a square box of size delta by 2. Okay, if you think, then this becomes delta and this becomes delta, and vertically also it is like that. So once I have this imaginary partitioning, then I have I have essentially some interesting point. Okay, so if you consider one box, its length is delta by 2 and its breadth is also delta by 2. So what is the diagonal of this box? So diagonal of a square box, square, is equal to how much? Square root of, this is delta by 2 square plus delta by 2 square. What is that? That is essentially turns out to be something like, actually, delta into how much is it? It is actually square root of 2 into delta by 2. You can think of like this. Okay, because there are two such, I just bring one out and it is 2. So square root of 2 is actually 1.414 into delta by 2 approximately. So this is actually, I can say this is less than delta. Okay, so that means uh, suppose uh, suppose that means if 2 points are there in this box, in any box, suppose any box, okay, so suppose in two points are inside any box, even if they're corner points along this diagonal, then their separation is actually smaller than delta, or they're potentially the desirable points. But there's a contradiction. We assumed this is not the case, because if you look at the region right of this line L, this is my line L. So this is my line L, right side is this region R. And for this R, I have already found out the closest pair recursively. That is my R0 star, R1 star. I have found out. But now you are assuming, okay, this division, so if there are 2 points in this, their distance is actually smaller than delta. So such a thing cannot happen. That means such 2 points cannot exist inside such a small square box. Quite similarly, such a thing cannot happen in Q actually. I mean, all the square box cannot have 2 points, because then in this Q region, I have already found out the closest distance, that is Q0 star, Q1 star. I have already found. So this thing cannot happen. So what does this mean? This means that in each box, there may be maximum 1 point. And also it should be in such a way, I'm interested in such a way that 1 point is in this left side or on the L, and the other point is always strictly in the right of this L. Okay, that means I am looking for points that say 1 point is Q here, then another possible point can be here, anywhere in this box. I mean, it must be my S, it must be my S prime, something like that. I mean, these 2 points, S and S prime, must be in both sides. It cannot be on the same side, actually. Because same side I have already found out by recursive calls. Okay. Now, with this idea, I ask that where this S and S prime can be. Okay. Let's say this S is at this corner point. Okay. Then this S prime, if it has to be to the right, strictly right of this line L. Okay. Strictly right of this line L. So it may be somewhere here, a little epsilon more than this L, or it may be here. Okay. Then what is their separation? Their separation is, this is delta by 2, this is delta, almost delta by 2, then this may be. But suppose they are at a separation of 15 separation away from each other. I mean, let's say it is slightly in the horizontal, it is here. Okay? Horizontal, suppose it is here. So this means it is delta, and this is another delta by 2. So if the horizontal separation itself is more than delta separated, their actual Euclidean separation will be more than delta. So that means that point delta, if one point I fix at a distance of here, this delta by 2, this side I cannot make it x separated more than delta by 2, because then their x separation will be more than delta, effectively leading that their Euclidean separation will, then they will just discard. So depending on my position of this, the S, the x position of this S star is limited. Okay, that means effectively two boxes I need to x direction. Now vertically, likewise, if there y, if one point is here, then definitely I cannot put the other point on the same side of L. I can put the other point on the other side of L. Let's say vertically it is more than, say, one box here. Vertically it is more than two boxes away in the right side. This is, so let's say the second point is here. Let's say this is my S, this is my S prime. You see, no, this is too much X. Let's say X separation. Let's say this is the point. Their X separation is delta. But since their vertical separation is actually again delta, so they're more. You say, I will make, no, I will make X separation as small as possible, but the vertical separation I will make more than delta. So let's say this is the point S prime. So what their X separation is, just maybe the, plus epsilon. But what is the vertical separation? Vertical separation is almost delta. Okay, almost 2, because this is corner, this is delta by 2, this is delta by 2. So vertical separation is delta. So even if this entire thing is epsilon, okay, then this is more than delta. One separation is more than equal to delta. That means overall separation will be more. But those points will not be need to be considered, because they do not give points which have whose Euclidean distance is smaller. Okay, so that means if for every point, if you make a sphere of radius, I mean, so two boxes in the x distance and two boxes in the right, in the vertical distance, if you make all such, so how many boxes in the x quadrant? 1, 2, 3, 4. You need to potentially check. Similarly, it has 4 quadrants, if you think. So 16 boxes. So 16 is again too much pessimistic. It can be shown that for some you need to check maybe 8, some you need to check more. So for every position S, you need to check actually constant number of other points S star, S prime in the right side. And remember, they must be, one point must be in the left of L, another point must be in the right of L. Okay, so this essentially proves the lemma that this thing happens. Okay, that, I think the rest is clear. I stop here today. We're out of time. Only 20 participants. Very poor.